All right, so today's question is a little bit different because rather than just being a direct question, it's more of asking us to do an experiment, and then it'll ask us to interpret the results or comment on them. So the experiment we're going to be doing is we're going to be rolling a die first 6 times, then another 6 times, and then another 6 times, and we're going to make up the probability distributions as we go. Now, before I do that, I'm going to put the theoretical probability distributions over here to give us an idea of what we would normally expect. So, first things first, I have this die. It has 6 sides. So if I roll it, there's no reason we should expect any one of the sides to come up more frequently than the other. So if I were to roll the die once, there's a 6th chance, right? There's 6 possibilities. One of those is that I roll a 1. And so there would be a 1 in 6 probability of getting a 1. So I'll just do my theoretical probability distribution here. For 1, 2, 3, 4, 5, and 6, all of these we would expect to get a 6th. Because I've got 6 possibilities and I roll it, I could either get a 1, I could get a 2, or a 3, or a 4, or a 5, or a 6. And as a decimal, 1/6 is 0.167, which as a percentage would be 16.7% about. And so we expect that for all of the die rolls. So let's go ahead and get to rolling and actually make up our observed probability distributions. Okay, so that's my first set of 6 rolls. That one really diverges from the expected probability. So I got 2 1s, so that would be 2 out of 6 total rolls. I got no 2s, no 3s, so that's just 0 on the probability. And I rolled 4 times, so that's 4 out of 6 for the 4. And then no 5s, no 6s. So you might be looking at that and going, well, a lot of good this theoretical stuff does then, right? Well, hold on. Let's go ahead and go on to the second set of rolls, and let me actually label these x's. x2, x3. Let's go ahead and go on to the second set of rolls. Okay, that's my second set of rolls. This time was a little bit better, more evenly spread out. I got 2 1s, so that's 2 6ths. 1 2, so that's 1 6th. 2 3, so that's 2 6ths. A 6th for 4, and then 0 again for 5 and 6. Okay, so let's go ahead and go on to the third set of rolls. Okay, so after those 6 rolls, I have no 5s, but it's even more evenly distributed. I got a 6th for 1, a 6th for 2, a 6th for 3, a 6th for 4, and then 2 6ths for 6. Okay, so what's cool is that even with these thinning out a little bit and spreading out more evenly, it totally could have happened that I would just get something like the first row roll over and over again, and that would not have changed. That could happen, right? But notice the more often I do this, the more I begin to see what we would expect theoretically. Now, one more thing we can do is we can tally up the totals thus far. So here I was doing a roll of 6, getting the probabilities, then a roll of 6, getting those probabilities, and then a third roll and getting those probabilities, and I was doing them on their own. But what we can also do is sum them up as we go. So if I do an x1 plus x2, so all the rolls up until the second point, then what I've actually got is 4 1s, there's my table, I got 4 1s, I still have 1 2, 2 3s, 5 4s, and still no 5s or 6s. Now, I didn't roll 6 times, I rolled 12 times, so the probability here of 1 and 2, that's going to be 4 out of 12, 1 out of 12, 2 out of 12, 5 out of 12, and 0 and 0. Finally, the other thing I could do is I could add up all three of the values that we had so far. So I'd have x1 plus x2 plus x3, right? And so I'm just going to take what I had, x1 plus x2, and add the third one in. So for 1, I'm going to have 5. For 2, I'm going to have 2. For 3, I'm going to have 3. 4, I'm going to have 6. 5 is still 0. 6, I got 2 times on the last roll. So the probability altogether, probability total, I'm going to divide these out of 18, because that's how many times I rolled altogether. 6, 12, 18. So I have 5 out of 18, 2 out of 18, 3 out of 18, 6 out of 18, 0, and 2 out of 18. And if I go ahead and calculate these right quick in terms of percentages, 5 out of 18, that's about 27.8%. 2 out of 18 is going to be 11.1%. 3 out of 18 is going to be 16.7%. So one of them matched the theoretical. 6 out of 18 is going to be 33.3%. 5 is just 0, so 0% for 5. And then 2 out of 18 is right here, that's the 11.1%. So for the total, when we did 18 rolls and compared them, one of our data values actually matched up. It was exactly what we would expect, and that was for a roll of 3. The other one shifted a bit, like for 2 and 6, we got a little bit less than we expected. 5, we didn't get at all. So the probabilities we lost on those kind of got put elsewhere. We've got a more likely chance of getting this 1 over here, and then the probability, or the probability distribution for 4 was 33.3%. So this all still adds up to 100% to the total sum of possibilities. Now what this shows is something called the law of large numbers. If you look over here for our first roll, the 2/6, that was a 33.3% chance of rolling a 1, and the 4/6, well, that was a 66.7% chance of rolling that. So those were really, compared to this, those were big probabilities, and we didn't get the other things at all. And so it wasn't matching up with the theoretical. But as I did more examples, right, 2 things happened. The second and third rolls were just more evenly distributed in general, right, and closer to the probability distribution we'd expect. And when we did it all as one thing, and I had 18 rolls all together, we had much more reasonable probabilities, one of them even matching the theoretical probability. And the thing to keep in mind is that even 18 rolls is not that many. It's not a lot of data to go off of. So there's something called the law of large numbers. And what that says is if I sat here and I kept rolling this die over and over and over again, right? So in other words, the number of times I rolled it became large, then what would happen is that these would get even closer to this value of 16.7%. I would start to see more 5s. That would bring that probability distribution up. The very fact that I'm seeing more 5s means I'm seeing fewer of some of these other numbers. So these distributions would go down. I'd see more 2s and 6s. And overall, if I could just roll this die over and over till infinity, I would see this 16.7% for 1, 2s, 3s, 4s, 5s, and 6. Now, of course, we don't have infinity time to sit around rolling dice, right? But as you might expect, even if I rolled it 100 or 1,000 times, this data gets a lot closer to the theory, like very close. So that is the law of large numbers, and that is doing this question where it asked us to write these out, do the probability distributions, and then comment on them. My comment on it is that the more I did it, the closer and more reasonable these probabilities got compared to what we would expect in theory, and that in general, the more you do an experiment, the more the values should approach the theoretical values. And that is this question.